you. So I'm going to present today a joint work with Anna Frischmann about forward and inverse fluxes in rotating condensate. So you will see what I mean by forward and inverse. It's not exactly what you expect. Let's just take a few lessons from the 2D world. So for instance, from those beautiful experiments on soap films that display Navier-Stokes equations in 2D, so 2D phenomenology. We know from the 2D world that there is an inverse cascade of energy, and the reason for this is that we have two positive invariance quantities, the entropy and the energy, which give us a law for an inverse cascade. And we know that energy condenses to the largest available scale to the system, so to the large scales, if you have small enough dissipation at large scale. We are also driven by the idea that in geostrophic flows, although I will make very few statements about geostrophic flows, geophysical flows, sorry, that there is a geostrophic balance that creates 2D structures. So rotation in 3D creates 2D structures, and that's the celebrated Taylor-Prullman theorem. However, the connection between those types of ideas is not necessarily clear. The reason for this is that if we consider a 3D flow governed by the 3D Navier-Stokes equation, we still have no law for predicting an inverse cascade, because we have invariant quantities that are the energy and the entropy, which is the dot product between the velocity and the vorticity, and the entropy has the helicity h is not sign definite. So if you don't have two sign definite invariants, you are not going to have a clear law explaining an inverse cascade. So what I'm going to consider in this talk is the 3D Navier-Stokes equations under a Coriolis force with a forcing which is 3D and random, and I will consider the viscous diffusion term. So I have no friction, but only viscous diffusion, and my problem is parameterized by the Rossby number, which is goes in 1 over omega, and the Reynolds number, and I will fix the energy injection of the forcing epsilon. So I will think of fixed energy injection in the system. So it is known, very well known, that the inverse cascade creates, and the Taylor column creates, and the condensate that is obtained at saturation of energy with time, it has the shape of a very robust Taylor column, invariant in Z. So these results were obtained by Seshasayana and Alexakis. So you have here a cubic domain, and Z is the direction of rotation. So we have here a domain that has a very finite site in Z. It's not a thin layer. It's really something thick. If you change a little bit the anisotropy of the domain in the x and y direction, so not the direction of rotation, while in this direction here, what you observe is different shapes of the condensate. I'm not going to talk much about it, but I know that our next speaker will develop that into the Navier-Stokes equations. But here we are 3D with rotation. We observe that either the condensate is made of jets, if you have a rectangular box, say, so anisotropy in this direction. So here jets are just linear profile of the mean flow that is very linear, astonishingly very linear. And in other configurations where you have isotropic domains, you observe actually dipoles. And in some cases, however, you also observe cyclones, and you have symmetry, you have only cyclones in your flow. And this depends on the regimes in Rossby number. But before going into much details, I will just consider a very simplified system, which is a linearized Navier-Stokes equations. And as we have understood from Eran's talk yesterday, rotation creates waves that are called inertial waves, which simply solve this linearized equation. So the very simple way to see it is that I take the Fourier transform of my equation and I curl it twice in Fourier, and this will give me a linear operator that is in the curl of U. So waves, the helical waves are waves that diagonalize the curl. So basically you have you can write your wave field as a sum of waves, with h being the eigenmode of the curl operator. So because of this operator, and so they diagonalize the k rod, and we know that the dispersion frequency that you obtain, the dispersion relation that we obtain, the frequency is a function of kz over k. So this creates this angular phenomena that Aaron told us. But an important thing here is that the frequency has a sign here, s. So I have two waves, one that propagates in the direction of k, and the other that propagates in the other direction, is the minus k. So it creates plus waves and minus waves, and these are reflected in the dispersion relation here, s. S corresponds to the sign of helicity, which is here the curl times the velocity, or h. Just a little bit of a remark here. We have here a signature of our beloved celebrated Taylor-Pullman theorem, because here what this dispersion relation tells us is that slow modes, so the ones with low frequencies, low omega, corresponds to low kz, so kz close to 0. So slow modes are 2D. That's the Taylor-Pullman theorem. Okay, let's take a look at a decomposition of the Navier-Stokes equations using this helical decomposition. So here, contrary to the former slide, I will consider that A is a time-dependent amplitude, and I will just project the Navier-Stokes equations onto this type of basis. It's just play on Fourier and on this helicity sign. So I will get a very, very traditional sum on the triads with my nonlinear term here, with a coupling coefficient. And this coupling coefficient depends on I mean, it's hard to see, but here this coupling coefficient has a prefactor here, which is only depending on the on the shape of the triad, and it depends on something close to p minus q with those signs. You can also notice here that there is a detuning frequency. I mean, there is a sum of frequencies that that actually simplifies a lot if I consider that one of my wave numbers is 2D and the two others are 3D. So if, for instance, k is 2D, so kz equals 0, and p and q are 3D, I have a simplified dispersion relation that is mostly in p minus q. So what we observe and what we know is that at quasi-resonance, so when this sum of frequencies is close to 0 or small enough compared to the rotation rate, you have two conditions for resonance. One is that the helicity signs are the same between the 3D waves, the p and the q's, they have the same sign, and the fact that in terms of amplitude, their amplitudes are very, very close to each other. And you can see from this that the coupling coefficient would then disappear, I mean decay, because it's in p minus q, so which tells you that 3D Navier-Stokes at very high rotation have a very strong tendency to decouple the 2D manifold from the 3D manifold. However, I just want to make a statement here. It doesn't predict at all the behavior of the flow, of the full flow, in the Rossby-Reynolds plane. It just tells you that 2D and 3D manifolds decouple. So let's look at our condensate. So our condensate, here, if I fix the Reynolds number, if I increase rotation, I would get through a series of regimes, 3D turbulence at very, very low rotation. And when I increase rotation, the Taylor columns form in the form of a condensate. You have cyclones, then you have jets that appear, and then at some point, the condensate disappeared at very high rotation. So I can see it here in my plot, which is the energy as a function of Rossby number. You see that the condensate saturates to some value that depends on Reynolds number, but then it slowly, in a polar law way, disappears. So with reinforcing, at fixed Reynolds number, the inverse cascade forms but progressively disappears when Rossby tends to 0. So this is very different from what happens when you force 2D in 2D. So if I force in my annulus in K-space. So this work was done by Sébastien, and you observe then in this case that at very low Rossby number, you saturate to a constant value, which is very close to the 2D-like case. And in the 2D-like case, what you have is very simple. You have an energy injection, and most of this energy will go to the condensate and will be dissipated by the condensate. So U over a squared is epsilon, mostly. You have a little bit of dissipation, but so which gives actually a situation where you would saturate with Rossby at a fixed value that depends only on Reynolds number. However, in the 3D forcing case, it's not at all what we observe, and we observe a decoupling that scales as Rossby number, and this is just an observation. We have no prediction for this. However, I want to point out that Taylor will be very happy about this result, because it's not a breaking of the Taylor-Pruman theorem. It has nothing to do with that. It has to do with the fact that the Taylor-Pruman theorem applies for slow modes. It applies for slow motion. So as here our waves are very fast, very 3D, they are not within the framework of the Taylor-Pruman theorem, which is a quasi-steady theorem. Okay, so if I do the other experiment, I just fix my Rossby number and increase my Reynolds number, I would observe that at finite values of Rossby, the condensate energy saturates with Reynolds number. And it saturates with Reynolds number as a function only of Rossby number. And this was observed both in 3D and in 2D forcing. So there is a fundamental understanding that we can make on this system that comes from Walev. Walev predicted and conjectured something very fundamental in 1991, which is that if you consider, instead of your sum of wave numbers, you consider only an elementary triad, and you apply a weakly nonlinear analysis, you consider the amplitude at 1K and you perturb the system, you would get stability conditions for the system. And what Walev conjectured is that the stability characteristics of these triad interactions are reflected in the statistical direction of the energy transfers, which means that if you do this analysis, the energy should go from the unstable wave number to the other two. This is a conjecture. This is a conjecture on the direction of the transfers based on stability properties of the triad. So what Walev could do then is that he could build 8 classes depending on the sign of helicity, sign of the wave numbers of the wave numbers. So you have 3 triads. They each have plus or minus. You have 8 classes. And what I will assume is to make a very, very simple conjecture, which is that the 2D mode is very small. It is the smallest mode in the system of triad. So it gives me...
Smallest by what?
Sorry?
Smallest by what?
So smallest compared to the other...
Smallest by in amplitude or the
in amplitude.
wave number?
In amplitude. In wave number amplitude. It has a smaller wave number than the 2 others. It's just...
In the wave number, in wave number.
Yeah. Not in amplitude. Yeah, sorry. In wave number amplitude. In the norm of the wave number. So this gives me 4 classes. So depending on the sign of the 3D waves, on the helicity sign of the 3D waves, plus or minus, I will have either an inverse transfer, where plus, plus, and minus, minus act with a 2D wave number, and another class which will predict me a direct transfer when you have the opposite sign of helicity. We call this a heterochiral transfer. It's too complicated word, so I will say plus minus. Plus minus gives a direct transfer, and minus minus or plus plus gives an inverse transfer. Okay, so I can just check this by computing the fluxes from the 3D Navier-Stokes equation. So just computing my fluxes, whether I have a 2D mode interacting with 3D, plus plus or plus minus. So first, an important notice is that most of the energy that goes to large scale, most of our inverse flux here, is dominated by 3D to 2D interaction. There is a little bit of the energy that goes that channels to large scale through the 2D manifold, but it's very small. Mostly things are dominated by 3D to 2D interaction. So this is the blue line I'm showing here. So I denote epsilon n the flux to large scale. And so, it's a bit complicated plot, but what happens when you distinguish plus plus and plus minus is that it gives you two channels, one being negative, plus plus has an inverse channel of energy, and a positive, a backward flux to the small scales that is predicted by my conjectures. So you have two subfluxes. It's a very, very peculiar thing. It means that the total energy going to large scale is subdivided between a positive contribution from the plus-plus waves and the negative contribution from the plus-minus waves, which acts mostly like a dissipation, an effective dissipation. So this is a very, actually has a lot of significance because what we can say from this is that in my Rossby-Reynolds plot that here I somehow, I just use another control parameter, which is Rossby times square root of Reynolds, which is basically a large-scale Rossby number. What happens at very low Rossby number is that you have no forward flux. You have only contribution from the same helicity signs. So plus plus or minus minus contribute to the 2D flow, but they slowly decouple. So basically they obey this very stringent resonance condition. You have the same sign in your 3D modes. And slowly, the total flux to large scale disappears, slowly. And what happens at high Rossby number, so at low rotation, is that you have an emergent forward flux that at some point equilibrates the inverse flux. So we get a very, 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 very odd situation where we have a flux, the total flux to large scale mostly tends to 0. But we still have a condensate.
Your forcing generates helicity or not?
On average, no. It's isotropic. So this state was observed in DNS recently. It has a tendency to create arrays of vortices, and I don't have a lot of time, but it's dominated by fluxes both in scale and in space. It's a very, very, very peculiar situation. But maybe I will just jump to my conclusions. So the inverse energy cascade progressively disappears as a power law of Rossby number, and this has only to do with waves acting with the same helicity sign. And if I fix the Rossby number, however, I will always tend to a regime where the flux tends to 0 because of these counterbalances fluxes, which creates a flux loop. And the question we want to ask is whether we can derive those results from quasi-linear formalism, but not there yet. Thank you for your attention.
There's a little bit of time for a question or two. Steve?
Are your results sensitive to the correlation time of the forcing?
We have not considered correlation times.
Is this delta correlated?
Yeah, it's delta correlated. So I don't know. Probably would play a role in putting in phase the helicity sign. I mean, it's yeah, I don't know. Yes.
So the 2D mode also has a sign.
They do, but I don't think they matter. I mean, like on average, the 2D manifold indeed has a helicity sign. If you think of the 2D manifold as a mean flow, then it doesn't because it's invariant in Z. But the class. Yeah, I mean, the conjectures that I made don't depend on the sign of helicity of the 2D flow, and I think it doesn't really matter because it doesn't appear in the dispersion relation. So the 2D flow has 0 frequency, so you don't really care about it. Thank you.
All right. Thanks for your